When two variables change together, we say they're related. But how do we measure that relationship? In probability, we usually rely on two key metrics, covariance and correlation. And these concepts matter in many fields. In finance, they help investors build better portfolios. In meteorology, they reveal how different climate variables interact. And in biology, they may help show how different traits co-evolve. And so let's build some intuition around covariance and correlation and understand how they shape real-world decisions. And to do so, let's meet Frank and Todd, two fictional characters offering you a coin flip bet. You'll flip a coin with Frank and a separate coin with Todd. These flips are independent, meaning one flip doesn't affect the other, and we'll revisit why that matters later on. Now, if it's heads for either bet, you'll win $100, and if it's tails, you'll lose $50. We'll refer to your bet with Frank as X, and your bet with Todd as Y for the remainder of this video. Now, for each of these bets, we can plot their marginal probability distribution, which simply shows the probability for each possible outcome X and Y can take on, which we'll refer to as X sub I and Y sub I. Now with these plots, we can now calculate the expected value or mean for X and Y, the average payout you'd anticipate if you played each bet many times. For example, to find the mean of X, which we'll call mu sub X, we can compute a weighted average of each possible outcome according to its probability of occurrence. Now this works out to $25 for both X and Y, which is exactly why Frank and Todd are running the bets. Otherwise, I'd be bankrupt in no time. And I should note here that if you want to learn more about expected values or marginal distributions, don't worry. We have two earlier videos covering these topics in detail on this channel. Now, so far we've looked at Frank and Todd's bets separately, their marginal probability distributions. But what if we want to understand how these bets behave together? That question leads us towards the idea of covariance. To get there, let's first create a joint distribution, a scatter plot showing every possible pair of outcomes for X and Y. Each dot on this plot represents one possible outcome pair, say winning $100 with both Frank and Todd, and the size of the dot reflects how likely that pair is. Now, because Frank and Todd's flips don't affect each other, the probability of any pair of outcomes can be found by simply multiplying their individual chances, an idea we covered in an earlier video on this channel, which I'll link here. For example, the chance of observing heads and winning your bet with Frank is 50%, and the same goes for Todd. Multiplying them together, the chance of winning both bets is 50% times 50%, or 25%. Using this logic, there are then four possible combinations of X and Y, each with a probability of 25%. That's why every dot on our scatter plot ends up being the same size. Let's now replot the scatter plot, but with the mean values of X and Y subtracted from each point. Now, why do this? By centering our data, we can see more clearly how X and Y jointly move relative to their individual means. And this brings us to the idea of covariance, which is the expected value of the product of how much X and Y deviate from their own mean values. In our discrete case, this simply means taking a probability-weighted sum of these products. More simply put, covariance tries to measure whether X and Y tend to move together relative to their means. For example, if both X and Y tend to be above their means or below them at the same time, moving together, their deviations have the same sign. Multiplying two positives or two negatives gives a positive product, which increases the covariance. On our plot, that's the top right and the bottom left quadrants. And conversely, if one is above its mean while the other is below theirs, their deviations have opposite signs. Multiplying a positive and a negative gives a negative product, which decreases the covariance. These outcomes fall in the top left and bottom right quadrants. So by seeing which quadrants dominate, we can quickly tell whether the covariance is being pulled upward, downward, or if it lies close to zero. For our coin flip bets, the covariance works out to zero, and that should make sense. Since the flips are independent, the ups and downs of Frank's bets don't systematically increase or decrease with Todd's. But what if we change the setup of our bets? Instead of two separate coin flips, there's now just one flip that applies to both Frank and Todd. And if it's heads, they both pay you $100. If it's tails, you lose $50 to both of them. Each character's payouts and their probabilities, their marginal distributions, stay exactly the same, but the probabilities of the joint outcome shift. More specifically, there are now only two possible joint outcomes that can occur. There's either now a 50% chance they both pay you $100, and a 50% chance you lose $50 to each of them. So let's now update our scatterplot with the probability of each possible combination adjusted. And notice here that the outcomes with non-zero probability lie in the top right and bottom left quadrants. According to our covariance equation, this will give us a positive value, which makes intuitive sense. When Todd pays you more, Frank tends to pay you more too, and vice versa. The outcomes of X and Y tend to deviate together. And let's now switch things up one more time. We still have just one coin flip, but this time Frank and Todd's payouts move in opposite directions. If it's heads, Frank pays you $100, but Todd costs you $50. And if it's tails, Frank costs you $50, while Todd pays you $100. Again, the marginal distributions for each character's payouts stay exactly the same, but the joint probabilities shift. This time, the outcomes with non-zero probabilities fall in the top left and bottom right quadrants of our scatterplot, resulting in a negative covariance. This happens because Frank and Todd's payouts move in opposite directions, and this shows us how covariance captures the direction of the relationship between two variables around their means. When they move together, we arrive at a positive covariance, and when it's in opposite ways, our covariance is negative. Now let's not change anything else about this situation except the payouts. Instead of winning $100 or losing $50, imagine Frank and Todd either pay you $75 or you lose $25. The sign of the covariance won't change. It still tells us whether X and Y jointly move together or oppositely, but the magnitude will change. That's because covariance depends on the scale of the variables, which is simply a fancy term in probability to describe dispersion. This means the magnitude of covariance is hard to interpret. A large covariance might just mean the variables have large units of range. And so what we need is an intuitive scale-independent metric that lets us easily compare how strongly two variables are related, no matter their units of scale. And that's exactly what correlation provides us. And I should note here that while there are multiple correlation measures, the most common is Pearson's correlation. It's defined as the ratio of covariance to the product of the standard deviations of X and Y. We usually denote these standard deviations as sigma X and sigma Y, which are the square roots of how much each variable deviates from its mean squared, weighted by the probabilities of each outcome. By normalizing covariance with the product of these standard deviations, we actually achieve three things. First, our measure of joint movement becomes unitless, making it easier to interpret and compare across different variables measuring different things. Second, the scaling doesn't change the sign of covariance, our denominator only adjusts its magnitude, which helps clarify the strength of the relationship between the variables. And finally, it ends up causing the correlation coefficient to be bounded within a very specific range. Referring back to our earlier scatter plots, when Frank and Todd's payouts are perfectly aligned, the correlation is 1. And conversely, when their payouts move in exactly opposite directions, the correlation is -1. And more generally, we know that our correlation coefficient between any two variables should lie between -1 and 1. So why do covariance and correlation matter? One practical way to see this is by looking at the combined payout of Frank and Todd, the sum of X and Y for each scenario discussed. Let's call this new variable Z. We'll start by revisiting the joint distribution of X and Y and focusing on the case where the correlation was 0. Remember, there were 4 possible joint outcomes, each equally likely. We could either lose both bets, losing $100 total, we could win one and lose one, resulting in a net gain of $50, or we could win both bets, totaling $200. From this, we can plot the probability distribution of Z and compute its mean and standard deviation, capturing its central tendency and overall dispersion. In this case, the mean is around $50 and the standard deviation is around $106. Now let's look at the case of perfectly positive correlation, the situation where a single coin flip either makes both Frank and Todd pay you $100 each or cost you $50 each. Here, the mean of Z stays the same, but the standard deviation increases substantially. This increase in dispersion makes intuitive sense. We either get a big payout or face significant losses. Finally, let's look at the case of perfectly negative correlation, the situation where a single coin flip means that if Frank pays you $100, Todd ended up costing you $50, or vice versa. If Frank cost you $50, Todd was paying you $100. Here, the resulting distribution has no variance at all. In fact, we're guaranteed to make money. Whenever we lose with one, we win with the other, and the expected payout of these bets remains positive. This is why, for example, there is such an emphasis on correlation and covariance in fields like finance. Combining things that don't move together can dramatically reduce downside risk. Now, one thing I still haven't really explained is why correlation is between -1 and 1. And it turns out there is a really neat connection between it and the geometry of vectors. And I suppose I could end this video asking for some likes if a follow-up around this topic sounds interesting. But to be completely honest, I've already started working on such a follow-up video. Either way though, thanks as always, like or subscribe to support the channel, and I'll see you soon.